Hey guys, and welcome to one more episode of Builder Nation. For today's agenda, we have Jonathan Sauder with us. He's a Deputy Manager, Office of Technology Infusion at the NASA Jet Propulsion Lab, and the Principal Investigator of a NASA project to design a rover for the surface of Venus. Welcome, Jonathan. Super happy to have you here today.
Awesome. Huge pleasure to be on the show with you as well.
Okay, so why don't we start this conversation by hearing about your experience, what you have been doing lately, about you, basically.
Cool. So, the highlight project that I've been working on is looking at how do we send a rover to Venus. And that is a big challenge because Venus is super, super hot on the surface of the planet. Nearly over 800 degrees Fahrenheit or 462 degrees Celsius. Which means most electronic components that we're used to don't work at those temperatures. In fact, paper would spontaneously combust on the surface of Venus. It's so hot if there was enough oxygen there to do so.
Wow, really interesting. And I was reading some article about it, and I've heard that before some people, the Russians, I think, they tried to go, but it didn't work. So what was the initial motivation? Why Venus?
So actually the Russians have successfully landed on Venus, but the longest they lasted was 1 hour and 20 minutes. Now I should note that was actually, an incredible amount of time for the technology that they had at the time and actually surpassed their mission goals by quite a bit as well. But basically to date, pretty much all the Venus missions that land on the surface are limited in time. And basically, you just wait until when you've got something that's 450 degrees Celsius, 460 degrees Celsius outside, you basically have to wait. You basically have the time until you get to that temperature. And once you get to that temperature, the electronics overheat and shut down and things stop working. So we wanted to look at building an alternate rover that could survive and even thrive in those conditions.
Wow. And what will be the other option if the electronics do not work there? Something like mechanical?
Right. So we initially went into the approach of let's build an all-mechanical steampunk rover. Basically, let's take Theo Janssen's Strandbeest, which you can, I think, see right up there, actually, was one of our inspirations, and thought, wait, this is really cool because there's something that, is entirely mechanical, responds to the environment. When there's danger that occurs, either wind speeds are too high, it can pound a stake in to keep itself fixed solid in the sand, or as it walks into the ocean, which is a danger zone for it, it can detect that and go in the opposite direction. And we were thinking, could we take the same concept that is, being done on the beaches of the Netherlands, built out of PVC and wind powered, and do the same thing on Venus, but make it out of high temperature metals, maybe? So that was where the initial seed of the idea started for us. And when we started to dig into it and design a system, and we're starting to come up with a system that was doing everything mechanically, from the science instruments to everything. Now, as we started to dig into the research, we realized there's actually been a lot of great work being done currently at NASA Glenn on high temperature electronics made out of silicon carbide and gallium nitride. The challenge with those electronics is their level of computational complexity is about that of a solar powered calculator. So those are electronics that can survive the 450 degrees Celsius, but they're both very power hungry and they're sort of big and bulky. And because of that, you can't get to very high levels of integration compared to other standard electronics. So we're going from, what we have currently technologically and back to sort of how do you build a rover that can run off the level of processing power of a solar powered calculator? And that's sort of what started us into the hybrid Automaton rover Venus design.
Wow, this is amazing. And how many people are currently working on the project, or how long has this been going on?
So it's been a pretty small team here at JPL. It's been about myself and 2 to 3 other full-time people or full-time engineers here and several interns who've been collaborating with this. And we've been working on this on and off for about the last 5 years. One of the things that we're constantly, challenged with, like any sort of NASA project that initially starts out, is funding cycles, right? And you have times where you get funding and you're working on it, and then you have to sort of apply for the next round of funding to keep raising what we call the technology readiness level, eventually to a point where we can propose the full-on mission to NASA. So right now we're sort of developing and sort of proving the proof of concept. And as we get opportunities to do so, we're pushing the technology forward to eventually where one day we hope to propose that mission and get a mission out there for a future opportunity.
Wow. Okay. And what does Harvey stands for? You changed the name, right? It wasn't the initial name.
Correct. Yes. The original name, when we were thinking about doing this all Strand-B style, was AREE, the Automaton Rover for Extreme Environments. So AREE. And the idea there is no electronics, throw them all off, the board and do something that's purely mechanical. What we realized, though, is we even found ways of getting data off the rover with radar retroreflectors, where you could basically be similar to semaphore. But if you have a very specific object that's very bright to radar, think like you take stealth technology and basically invert it. So instead of having something have a small radar signature, you have something have a really bright radar signature. And we were able to actually show that you could get bits of data off the rover using that. The challenge we realized, though, is that the data rates and the amount of things we could communicate would be very, very slow rates and really would not justify the cost of the mission for the amount of science data that you could get back using that. And that's where we moved into looking more at the high temperature electronics. And that brought us to the hybrid design of using these simple sort of, level of complexity of a solar powered calculator electronics and combining that with a mechanical system to develop something that could actually get some good science data and continue to transmit that information off the surface of the planet Venus. And that's what generated into the hybrid Automaton Rover Venus, or Harvey, as we call it. And we all like the name Harvey a little bit better. One of my interns came up with that, actually. And it is a little bit more anthropomorphic, which is fun.
Wow. So the actual prototype, the initial prototype has really changed over time. How many years has it been? Like 5?
Yeah. So roughly over the last 5 to 6 years, it's gone through multiple iterations. But, that's one of the things I guess I believe that's really important in engineering in general is to build and fail early and often, with the idea being that if you build a prototype, figure out what works, what doesn't work, and then you modify the design to sort of work within the new constraint space. And we've gone through about 5 or 6 different iterations of different types of prototypes and designs, right? We started off with a Strand-B style walking robot, which looked super sick and cool, but we actually had a study here at JPL where Theo Janssen, the creator of Strand-B, was nice enough to volunteer his time, come out and actually advise us on it. And one of the things he mentioned is, you want to move away from the legs, because while they work great on flat, sandy beaches, if you start getting to things that are rocky and indeterminate terrain, it doesn't do good in those type of obstacle environments and will either get stuck or could potentially tip over. And then we started looking at other concepts, and initially started looking at tank tracks per his suggestion. And we came up with an image that you've probably seen online where the Harvey looks a lot more like a World War I tank, which was, the idea was you could build something that was really robust and climb over obstacles, could flip upside down and keep driving. And the other thing that's actually really cool is even if you drove off a cliff, you could probably design your design of the drag of the rover that actually, if you drove off a cliff and if you have a wide enough surface area, it would just sort of float down, because Venus is a very, very dense atmosphere. So you could actually design it such that you wouldn't even have issues with driving off cliffs. The problem we ran into with that design is the issue of sort of a rock between the eyes. You have 2 tank tracks on either side, and if you have a rock in between those two, you would still have to detect that obstacle and avoid it. And we realized, as long as the tank track would hit the rock, it could go over it. But if we got stuff that was in the middle, that wouldn't work. And we needed space for the wind turbine to catch wind as well. And so that's what sort of made us realize that concept didn't quite close out for what we were looking for. After that, we moved to a Russian inspired design from the Marsakhod and Venerakhod rovers that the Russians had actually done some initial ideas on that and started looking at that design, but the actuation approach that was too complex for a mechanical system. And that's where we ended up at the current design for Harvey, which is a 4-wheeled rover with compliant wheels that sort of serve as your shocks built into the wheels that can overcome most of the obstacles that we believe we would see, and could drive about 100 meters before it would need to change course based on sort of a worst case statistics on the rocks that we'd see on Venus. So.
Wow. So it has dramatically changed. I did see the videos and I was like, wow, it's really different how it has changed, like the initial prototype, the legs that you're saying, and then it's really bigger, it's thicker, it kind of looks like, for a mortal like me, like a Wally or something like that,
Uh-huh.
from first seeing it. And I was like, wow, it has changed. And I can imagine how many, like ups and downs you have been through with your team. And that leads me to the second question, how is the transmission, like, how does that part works? Because that needs electrical engineering, right?
Correct. Yes. So that's where we use the high temperature silicon carbide electronics. So there's some folks at NASA Glenn right now who are actually developing there's this mission called LISSI, which is basically a weather station that is, sort of a small weather station that would sit on the surface of Venus. And there's a lot of good technologies being developed for that, that we could then use on the rover once that is fully developed and demonstrated. So that's currently still something that's being developed and proven out by NASA Glenn. And along with that, they're developing a high temperature silicon carbide transmitter that would be able to transmit information off an object on the surface of Venus. Now, the approach that we'd be using for this is a lot simpler than what current space missions operate in, where basically what you do is you'd be cycling through various scientific information and continuously transmitting the results. So basically, you're just sort of going through, here are the different things we're observing, and we're just sort of reporting on what are we observing, and then you repeat that cycle every several hours or so. And basically you're sort of constantly changing what instruments you're reporting on. And the idea there is you're making the logic very simple so that you don't have to have very much complexity, because you're really limited at the computational capability of those high temperature electronics that exist. But, to sort of summarize what Harvey does and what we've done with Harvey, you sort of divide the rover into two systems. We have the mechanical system, which does a lot of the power management, taking the Venus wind in and enabling us to do the mobility, finding obstacles, and figuring out how to safely move around the surface of Venus. And then we have the electronic system, which is mostly collecting scientific data. So sort of in an observe and report mode. And that's all sort of collecting information and reporting it to an overhead satellite as far as what we're seeing and what we're observing as we go through the Venus environment.
Wow, this is really cool. I mean, I know that you're super used to saying this, but I mean, hearing it sounds really crazy. And how long does the data takes in order to, I mean, how long does it takes you in order to receive the information?
So there would be at least like a 7 to 8 minute delay due to the speed of light in the best case scenario. It does depend exactly how the orbiter infrastructure is set up on Venus. Right. One of the things is, unlike Earth, where we have a bunch of communication satellites in orbit all around us, right, where there's multiple satellites that you can communicate to at any one point in time. The challenge with Venus is there's probably, only one, maybe two orbiting spacecraft when this mission would get there. And we may have to bring that orbiting spacecraft with us, which means that we may have very limited windows when that spacecraft is overhead and when we can actually transmit. So with that, there's going to be, limited windows where we can pick up that data, and then you have to wait for that spacecraft to get on the right side of Venus to then transmit back to Earth as well. So, the rate at which we get the data will definitely vary depending on what exactly the orbital infrastructure looks like and how things are set up. The actual time to communicate from Venus to Earth is 7 minutes, but the time to get that data off the rover onto the orbiter and have the orbiter in a good place to communicate back to Earth, that could take, hours or days, depending on where you are at.
Wow, this is impressive. Okay, and how long do you think that? I mean, how many years or months or I don't know? Do you have like an estimate in order to finish this project, if we can put it like that?
Right. So as far as how long will we live on the Venus surface for? Our goal is to be on the Venus surface for one Venus diurnal cycle. So one of the things that's really interesting is Venus rotates very, very slowly. And equivalent day to night cycle actually on Venus, or a diurnal cycle, where you go from sunrise to sunrise, is 120 Earth days. So you go through a long period of night and then a long period of day on Venus. And the goal would be to have the rover operating that at least one of those 120 Earth day cycles, so we could see how does the atmosphere and the environment vary across day to night, to understand how does day and night influence things on the surface of Venus, which is something we don't know with the landers that have only lasted for a few hours with our current data set. But the goal of this mission too is to design a rover system that could operate for much, much longer. Most of the JPL rovers, right, their original mission was, 30 or 100 or, several hundred days, right? But a very limited time span versus the years most of them have lasted. We wanted to take an approach for a Venus rover that could have the same effect, where it would be able to operate for much, much longer on the surface of Venus and have many extended missions, and hopefully operate for, a full year, if not even longer, potentially exploring the surface of Venus. So, but I think you also had sort of another part to that question, which is, when might we see this mission and when might it launch, correct?
Yeah, you're answering my questions. Go ahead, Jonathan.
All right. So yes, so one of the challenges with space missions, we're still very early in the development process of it, and still very much, we're not quite ready to propose the mission to actually discovery or new frontiers or a funding source like that to get sort of full-on funding that would eventually go. So we're definitely in the pre-proposal phase right now for this mission. And the path from that pre-proposal phase to actual implementation is long and full of broken dreams, to be realistic about it. Most people in NASA get one mission that they were really a big driver for per lifetime, if they're lucky. That's if you're lucky to get selected. And there's been a lot of people who have been, putting their entire life into missions and haven't seen it selected. And that's because, the number of cool things to explore are so vast and so incredible in space. And at the same time, funding is definitely limited too, that we can only explore so many options. So we're definitely limited in where we can go and look to things. Right now, the key thing that we need really to move this concept ahead is we've developed a lot of the baseline technology, but we need to know more about Venus. So we're sort of actually waiting on other missions to Venus right now before we can start fine-tuning the rover to design it exactly to what we expect the Venus conditions to be like. And what's really exciting, in the last year and a half, there's been 2 missions selected for Venus, Veritas and Da Vinci. Veritas will be an orbiter that's going to orbit Venus and has an amazing radar on it that's going to reveal a lot of Venus secrets. Da Vinci will actually be a mission that goes through the atmosphere and possibly gets down close to the surface as well. But the main goal is to probe the atmosphere to help us understand more about the atmosphere. And then critically for us, that may help us understand more about the winds on Venus, which we're relying for a source of power. So after that, there's probably another 1 or 2 missions that we need to have happen, including a lander. And if you sort of look at and then after we get that lander, then we could look at really proposing this mission to move ahead. If you look at other, planetary exploration too, the progression is sort of the same. You first start off with orbiters that are flying around the planet. Then after that, you often get probes, which usually sort of go in and crash land on the surface and sort of get data as they're coming in. Then after that, you get landers. And then after that, you get rovers to explore the surface. So, we're sort of seeing that progression also with Venus and sort of the missions that are being selected. And the idea is to have our technology ready there when we're ready for a rover on the surface of Venus, that we've got the concept together and ready to go to propose to those opportunities. So as far as the timeline goes, we're looking at least 15 years probably before, we'd be looking at a launch if everything goes in the best case scenario. Chances are it could easily be decades longer than that. But, our job is to keep pushing that forward and keep pushing the technology forward to a point where when the Venus rover is needed, we're ready with the concept.
I love how optimistic you are about this. Wow. Yeah, I'm pretty sure that, for us mortals, we might see a project, NASA launching something or, and we're like, okay, this is great, the new improvement. But most of us do not know the reality behind it and the hard work that comes, behind each process and behind each research. So this is, definitely, I'm sure that I will see this before I die, hopefully.
Yes, and that's one of the incredible things too. When you see a NASA mission launch, right? Realize that there's been engineers working on the design of that for at least 10 years. And prior to that, there's been a scientist working on the idea for that mission for decades, probably, anywhere from 10 to 20 years. So missions start out 30 years, before they actually launch. So when you see a NASA mission going up, right, realize it's not just, someone quickly launching something really cool into space, but there's been decades of effort behind this to get it to where it's at, which is incredible.
Which is incredible. And just like you're saying, each mission is helping you to develop this one that you're currently working on. So, that's great.
Yeah.
Are there any critical challenges that you have, might face when it comes to the procurement process while building this?
So, I guess maybe not a whole lot for the procurement process. Actually, one of the really cool things we were able to do in this technology development, which was a really cool take on procuring ideas for the technology, is we were able to run a prize challenge to look at new innovative ideas for how we could detect obstacles. We need to have a mechanical obstacle detection device. And I had a team of very few engineers at JPL here. So we could come up with like 1 or 2 ideas on our own, but they probably wouldn't have been the best ideas. So what we realized is the best thing to do is sort of crowdsource this and get a bunch of great ideas on this. It sort of gives you a way of failing early and failing often on a bunch of different concepts by doing a prize challenge or getting a bunch of people involved. The other thing that's interesting too is it's very hard with the way government funding is set up, is for us to procure ideas from outside of the US. It's easy to set up a contract with a vendor in the US, but setting up a contract with vendors outside the US require a lot of extra paperwork and a lot of extra challenge. But with doing a crowdsourced challenge, there's sort of a shortcut around that where you can get ideas from all around the globe. So we were able to set up this prize challenge. And over the course of 5 months, we had an online forum where we had over 1,000 interactions with different people working on these concepts. And we ended up coming up with 5 really great, really unique ideas from Egypt, Latvia, Australia, United Kingdom, and the US, of course, too, that were able to contribute ideas to this to help us solve how do we detect obstacles in new ways. So that was a really cool, innovative way to go about procuring a set of ideas to give us the initial ideas and sort of crowdsource innovation in this to get around a really hard challenge. And it's awesome now because now these people have made a contribution to this mission concept, right? That will continue to live on in this mission idea as it moves forward, which is incredible. I should note, NASA has an active prize challenge program. So while this challenge for the Venus rover is over, if anybody out there listening to this podcast is interested in contributing ideas to future NASA missions, look up NASA prizes and challenges. And there's usually a few ongoing prize challenges throughout the time where you're a tinkerer or garage inventor or even a small engineering company. You may want to take a look at that and see what ideas you can contribute. And maybe you'd win a little bit of money if your idea is successful. And if nothing else, you get to have a fun time working on a hard NASA problem.
Wow, this I didn't know that this existed. I mean, this is great.
So this right here, all right, is a representative rover prototype that you may have seen on the Seeker video, which was designed to prove some of the key concepts of the mechanical Venus rover that we had. So what you can see in the front is a series of springs here, which drive the rover. Then we have the planetary reversing gearbox right here. And the primary purpose of this planetary reversing gearbox is the mechanical logic brain in the system, that when the rover detects an obstacle in the front, it will basically trigger the this planetary reversing gearbox and cause us to back up for a limited amount of time and then drive forward again. In the front of the rover, you can see we have a bumper on the front, which detects obstacles. There were a number of really awesome, great concepts for how to better detect obstacles in the HeroX Exploring Health Challenge. So that was the key challenge. And and so that we were able to test this at Venus temperatures and show that the basic concept of this mechanical rover worked at Venus temperatures. Now you'll notice this looks really weird versus any other rover because it's like really long but skinny. And the reason for that is the chamber that we had to test this in Venus conditions was a 12-inch diameter tube that was about 12 feet long. So we had to design a sort of weird hybrid rover that would prove the concept but fit in that exact volume. So this goes back to the point about sort of prototyping early and often. And another thing about prototyping that you need to do is you need to figure out how you build the prototypes to prove exactly what you want to test. In this case, we really wanted to show the mechanisms working at the extreme Venus conditions. So we built something that didn't look like a really regular rover, but was designed to specifically test the core functionality in that Venus chamber.
I'm shocked. And it survived the 400 degrees Celsius?
Yeah, 462 degrees Celsius. That's actually, so it's really fascinating. You notice this looks sort of brownish in color. It used to be shiny metal before that, but when you go to that temperature, so it used to look like more like chrome or, reflective steel. It turns to this sort of brownish purplish color at those temperatures. So it's really fascinating that everything gets this new look on it that gives it this very aged look when you're operating at those extreme temperatures.
And how many times did you place it in the chamber?
So we did like 2 or 3 tests in a chamber. Some of the first ones didn't work, and we had to problem solve some things in order to get it to operate in those conditions, of course. So.
Wow, this is great. Oh my God, Jonathan, thank you so much for showing it. This is amazing. And it's huge. It looks bigger than I thought that it would.
Yeah, so, well, the actual rover itself would be much bigger than this too. This is, just like a small scale proof of concept. The actual rover itself would be the size of a Mars rover, roughly. And so you're looking at the size of basically a small SUV. And one of the big reasons for that size is so that we can get a wind turbine up high enough to capture the wind that's traveling at a high enough speed to really produce good power for mobility.
Wow. Is it heavy?
This right here is probably about 40 pounds or something like that, 30, 40 pounds. So it's all made out of steel. So it's, not lightweight. Most spacecraft structures we build are aluminum, which is much, much lighter than steel. But the problem is aluminum loses all of its strength at Venus temperature. So you can't actually use aluminum at Venus temperature. In reality, when we go to Venus, we'd probably be making most out of titanium, which is lighter weight than steel. But titanium is very expensive and very hard to machine. So for the first prototype, we built it all out of steel, which will survive at the Venus temperatures. And we just end up with something that's a little bit heavier, but that's fine for proving out the concept here on Earth.
Wow. Jonathan, I mean, of course, I'm including this in the interview. I mean, thank you so much. This was great. The last question, do you have any advice for anyone who's interested in the space industry or in the robotics field, or, maybe just want to be an intern at the JPL laboratory?
Right. So I'll give you an answer specifically for people who are in mechanical engineering, maybe, if that's all right. And what that is we love to see people who have hands-on experience and love to tinker and build things. So the more opportunities you have to build things, whether that's, in an extreme example, you could go work on a NASA prize challenge, but other examples too, either at your university or with local clubs or hobbyists, if you like to work on cars or fix up houses or build your own inventions, those are all things that are really helpful and build a great skill set as an engineer to show that not only do you have the theory and the educational background to solve problems, but you also have the ability to apply that practically. And that's what we're looking for in a lot of people. I guess more generically too, one of the big traits I see across engineers at JPL is persistence and hard work. Not being afraid of showing up and doing the hard work, and being willing to persistently work at a problem despite whatever obstacles you face. Because in space is hard and there are tons of obstacles. So you need to persevere to get through it.
I still love how excited you are about challenges. That's great, Jonathan. That's great. Well, thank you so much for being here today. I really appreciate hearing your experiences, hearing everything about your project, which is really, really interesting. And I mean, do you have any social media handles where we can follow you, where we can find you?
Yeah, so I'm primarily most active on LinkedIn. I also have a Twitter account that's somewhat active as well. And I think both are just Jonathan Sauder, like my first name, last name. So
I know that you have your own personal website, right?
Correct. Yes. So you can go to jsauder.com, where I've got a personal website that sort of highlights a little bit of my background, and also I post any recent news articles on different things that have been posted to on that website. So
exciting. Thank you. We'll make sure to follow you on there as well. And remember, guys, that you can also find more information, interesting articles, interesting interviews, just like this one with Jonathan, directly on our website, controlhub.com/builder-nation. You can find us there. And once again, thank you so much, Jonathan, for your time. We really appreciate it.
Awesome. Thank you for the opportunity.